In this video, we'll look at how to solve 2x2 systems using substitution. So here we have an example of two linear equations. The first one, y equals negative 1/2 x plus 1, and the second, y plus 2x equals 10. So we talked about in the last video the fact that we're looking for the set of ordered pairs that work for both equations. But sometimes graphing the equations isn't that user-friendly because your lines can be difficult to graph. They can have large y-intercepts, or they might not intersect at a nice point. Maybe that point is a fraction, so it might be hard to read the point of intersection. So we have two algebraic methods which don't involve graphing. The first one is called substitution. So let's take a look at this example. I have it written out here as well. So remember, we are looking for a solution, an ordered pair. So our ordered pair will be some x, y that make both of these equations true. So whatever the x and the y coordinates are for the first equation, they have to be the same for the second equation. So in order for us to find this point, we need to think about whatever y is here, it's got to be the same value here. And likewise, whatever x is here, it's got to be the same value here. So we're going to use that fact, and we're going to take our two equations and really put them together and solve one equation. Again, I always like to label my equations. It just helps me to keep track of everything. So here's my first one, here's my second one. Now you might notice that in this first equation, the y has already been solved for. So even though I don't know what y is precisely, I know what y is in terms of x. I know y is or equals negative 1/2 x plus 1. So that means that this y has to be the same thing. So since y is equal to this expression here, that means this y is also equal to that expression. So we're going to substitute this expression in for y in that second equation. So my second equation will now look like so. So sometimes we draw a line just to kind of show that we're resetting or reworking our system. And I'm just labeling my equations just to help you keep track. So my second equation will now have this y substituted as negative 1/2 x plus 1. I'm going to put that in parentheses. It may or may not be needed, but it doesn't hurt to put them in. That's what I'm substituting in. And then I'll continue the rest of that equation. Plus 2x equals 10. So my second equation now still has that same relationship, but instead of the y, we're putting in like a stunt double for y. Right, now I don't have anything that's multiplying y. There is no coefficient for y, so I can get rid of those parentheses and combine any like terms. So negative 1/2 x plus 2x, I'm thinking 2 plus negative 1/2, or 2 minus 1/2 is 1.5. 1.5 can be written also as 3/2. So we want to keep improper fractions as opposed to mixed numbers. You could use a decimal in that case. So that's just combining those two like terms. 3/2 x plus 1 equals 10. This is a linear equation with one variable, so I'm just going to go ahead, I'm going to find out what x is. I'll subtract 1 from both sides. 3/2 x equals 9. And I could solve this by multiplying by the reciprocal of that coefficient. Instead of 3/2, I'll multiply both sides by 2/3. 2/3 times 3/2 is 1, so I have just 1x. On the other side, 9 times 2 is 18, divided by 3 is 6. So I have x so far, right? So for my solution, I know that the x is 6. I need to find the y value. Well, I could find the y value by taking either of my original equations, because once I know what the x is, the y will match up, and it's got to do the same thing for both equations. So it really doesn't matter which one you pick, because you'll get the same result no matter which one you choose. So I'm going to pick the first one because it's already solved for y, and that's the variable that I'm looking for. So in my first equation, I know that y is equal to negative 1/2 x plus 1, and I'm going to plug in the x value that I know to get the corresponding y value. Y equals negative 1/2 times 6 plus 1. Half of 6 is 3, so negative 1/2 of 6 is negative 3. So y equals negative 3 plus 1, which is negative 2. So it tells me that the ordered pair, the solution, would be 6, negative 2. And I could write that, I put it back up top, but I could write that in set builder notation. The set of all x, y, such that x is equal to 6, y is equal to negative 2. And if you wanted to, you can check both of those solutions, or this one solution in both equations, and it should work for each one. So let's take a look at a general strategy for solving by substitution. So what was really important for that last example is that the first equation was already solved for y. So if you don't have one of the equations solved for x or y, you're going to take one of the equations and make it x equals or y equals. You choose whichever one is more convenient for you. Then you're going to substitute the expression for the isolated variable into the other equation. So once you have x equals or y equals, whatever's on the other side goes into the other equation. Solve whatever equation you have, and then use that value to solve either of the original equations for the other missing variable, and then write your solution as an ordered pair. All right, so we have two examples here that we'll get through. Let's start with the first one. All right, so I have both of my equations written out, and I've labeled them 1 and 2 just to help me keep track. My first equation is already x equals, which is nice because I don't have to deal with that first step. Since I have my equation solved for x, I'm going to replace the x in the other equation with the expression. When you rewrite your equation, which is the second one here, you should only have one variable. So I have now in parentheses 2/3 y, and then minus y equals negative 3. So notice my equation only has one variable in it. If it doesn't, then go back. So multiplying here, 3 times 2/3 is 2, so that's 2y minus y equals negative 3. Continuing to solve for y, I have y equals negative 3. So I have the y. Now I need the x that goes with it. So I could find the x from either original equation. Since the first one has x isolated, I'll use that one. If you like the second one because you don't like the fractions, then use the second one. So x is equal to 2/3 times negative 3. 2 times negative 3 is negative 6, divided by 3 is negative 2. So the x value that matches with that negative 3 is negative 2, which is your solution. And you could go ahead and write that in set builder notation. And check, if you want to check both of your equations. Our last example we have here. So notice that neither of these equations are solved for x or for y. I'm going to label these. So I have to pick. I have to pick either the first or the second equation, and I have to pick either x or y. So make the work easier for you. If you have a coefficient of 1 or negative 1, I would go for that. So I see that my coefficient for x in the second equation is 1. So it's just one step for me to isolate that equation. So I'll go ahead and do that one. So x plus 2y equals 0. Just subtracting 2y from both sides. So that second equation is now x equals negative 2y. If you wanted to, maybe go back and write your system. So I'm going to write the first one here. I like to kind of keep them together. It just helps me when I'm substituting. So this x is equal to negative 2y, which means so is this one down here. So this negative 2y will get substituted in here, and then I could have an equation with only y in it, which I will then solve. So let me bring this up here for some space. So that first equation is now 2 instead of x. I'm replacing that with negative 2y. So 2, and then my substitution, minus 4y equals negative 2. Oh, it's positive 2. So then I'll continue to solve. Notice that I only have y's, so I can solve that equation for y. 2 times negative 2y is negative 4y, minus 4y equals 2. Negative 4y minus 4y is negative 8y, which is equal to 2. And then I'm dividing by negative 8. Be careful with the division here, so don't just divide whichever way is convenient. It's 2 divided by negative 8. So I'll simplify that. That's negative 1/4. So my y value is negative 1/4. It's a fraction, which is a good thing that I did this one by substitution and not by graphing, because graphing could be a little bit of an annoyance if I have fractions. I do need to get the x value that goes with this. You can use either the original equations or any equivalent version. So I like this version of my second equation because it's already x equals. I've done some of the work already, so why not use that? So my second equation here said that x equals negative 2y. If y is negative 1/4, then x is negative 2 times negative 1/4. And x is negative times negative is positive. 2 times 1/4 is 2/4, which is 1/2. So it means my ordered pair, let me go back to that set builder notation, my ordered pair, x comma y, would be such that x is equal to 1/2 and y is equal to negative 1/4. So if I were to draw both of these lines on the same set of axes, this is the point where they would meet at 1/2, negative 1/4, which might be hard to read off the graph. Maybe if you graph it, you might be convinced that that makes sense. But from the graph itself, it's hard to kind of pinpoint those fractions unless you're writing your graph to scale, which is hard to do by hand, not necessary. In the next video, we'll look at the third method, elimination.